Thank you for joining us for the 2025 California Fire Science Seminar Series. And today is the last and the bonus webinar we have. So my name is Hanghui Chen, and I will be your host for today. I am a member of the student committee who assisted with the organization of this seminar series. And I'm a graduate student in the University of Science and Technology of China, studying fire science. And I'm really excited to be here for this talk we have today. The California Fire Science Seminar Series is organized and supported by the California Fire Science Consortium, the Fire Research Group, the University of California, Berkeley, and the University of California, Merced. Student committee was also integrated to the success of this series, which including 18 students and postdocs from across the USA and even across the world who helped select speakers and topics for this series. And this webinar is being recorded and will be posted on the California Fire Science Consortium website and YouTube channel. Following today's presentation, there will be a Q&A session, so please feel free to add any question you have to the Q&A box throughout the whole presentation. It's my pleasure to introduce today's presenter, Professor Sandy P. Harrison, who will be discussing model wildfires, key issues, new approaches, remaining challenges. Sandy Harrison is a professor of global paleoclimates and biogeochemical cycles at the University of Reading, UK, and a leading expert in land-atmosphere interactions, vegetation modeling, and paleoclimate reconstruction with a focus on fire disturbance, plant trace, and benchmarking climate models. Her works on wildfire focus on the analysis on the control of wildfire behavior on different timescales and the development of new models to capture this behavior. With that now, please join me in welcoming Professor Sandy P. Harrison.
Thank you. I'm really glad to be with you today and to talk to you about modeling wildfires. I want to stress that I'm talking about global models rather than local models, but I want to also look at some of the key issues and the new approaches and remaining challenges in modeling wildfires. If I can, right. So I think we're all aware that there have been some recent changes in wildfire behavior that are quite alarming. We've had fires in places where we haven't normally had fires, like the big Swedish fires a few years back. We've had fires that have lasted for much longer than normal because they're not dying down during the evenings. And we've had fires that have been totally catastrophic, like the recent fires in Greece and also in California. And I think we're also all aware that these changes in wildfire behavior are due to climate change, ongoing climate change. And that raises the issue of how ongoing climate change in the future will impact wildfire regimes. This led to the publication of a UNEP report a couple of years ago, which said that burned area will increase by between 20 and 40% by the middle of the century, and that catastrophic fires will increase by a factor of nearly 1.5 by the end of the century. Now, the thing about this report is that it's based on a series of models of the coupling between vegetation and fire under a number of different RCP scenarios of what the future climate may be. So this raises the issue of how well these models can actually capture fire today and how well, therefore, their predictions of the future are likely to be reliable. So a few years back in 2020, a group of fire modelers in FireMIP decided to make an evaluation of the models that we were using. And we were very happy at that time that we were in the ballpark for simulating burnt area. So the figure on the left here shows in the top the observed burnt area over recent decades, and then various different models, simulations of that. Now, there are a couple of models in there that were very old, so MC2 and GlobFirm, and they didn't do very well. But for most of the other models, we were in the ballpark. The simulated burnt area was between 381 and 536 megahectares, and that is really where the observations were taking us as well. So we were all full of congratulations for ourselves. And then we thought we better test this a little bit more thoroughly. And we wanted to test it against two sort of models, a random model, i.e. that we could distribute the observed burnt area randomly and do better than that, or a mean model where basically we took the mean fire across the globe and put that everywhere. And under these two models, a perfect agreement would be with the observations would be 0, and an agreement with the mean model would be 1. And we took this off from a benchmarking system that was first created for evaluating vegetation models. Okay, now when we do that evaluation, you can see that the models don't do very well. The brown colors here represent simulations that are worse than random at predicting burnt area or the seasonal phase of burnt area. The yellow means that they're worse than the mean, but they are better at least than random. And one of the things you can see here is that in terms of the seasonal concentration, the seasonal phase, and the interannual variability of burnt area, most models are worse than random or somewhere worse than the mean. Even for BA, there are very few models that had a perfect match to the observations. Very few were better than about 0.25 from the mean. So in other words, these models were not really doing a good job of most of the aspects of just burnt area. They're getting the spatial patterns okay, but other features of the burnt area, they were doing very badly. Now, I gave a talk about this some time ago, and it was pointed out that these are actually quite old models. I mean, the paper was done in 2020. However, we've also just recently done an evaluation of the models that are being used in CMIP6 that are fire-enabled. And again, here's a comparison of the burnt area fraction observed and the fire emissions observed on the left, with CMIP6 in the middle and CMIP5 on the right. So we were congratulating ourselves that we were better than CMIP6. You can see that the correlation coefficients have gone up quite considerably for CMIP6, but nevertheless, we are still, these models, these coupled models which are being used to do climate predictions, are still overestimating emissions and still underestimating the global burnt area. And you can look at individual models and you can see that there's quite a variability between the models in terms of burnt area on the left and fire emissions on the right. This is not just simply a function of the fire model that's being used. The G's on top of some of these columns represent variants of the GlobFirm fire model. So there is an interaction here between how well the models are doing in terms of their climate, vegetation, and then the fire. But nevertheless, what you're seeing here is that most models are underestimating burnt area. And even if they're getting the emissions right, there's still a number that are not. So this is quite worrying because these are the models we're using to predict future fires. It gets even more worrying when you start looking at the seasonality and the trends that we've seen. And so again, this is from the CMIP6 simulations. The plots on the left are showing the seasonality in terms of burnt area and emissions, where the black lines represent the observations and the various colored lines represent the models. And it's going from the high northern latitudes at the top to the mid latitudes of the southern hemisphere at the bottom. And what you see is that the seasonality in the models is not capturing what we actually observe. Sometimes they're out of phase. There's a gap of up to 2-3 months between what the models think is happening in a fire regime and what the observations show. And sometimes they're in phase, but there's a lot of uncertainty around what the models are simulating. And if we look at the long-term trends, which is the two plots on the right here, you can see the grey bars represent the observed trend in recent decades, in both burnt area and emissions. And you can see that it's very rare for a model to get the right sign even of those trends. And even if it gets the right sign, which a few of them do, very few, only one of them is really getting the real observed trend in burnt area, even approximately. So there's a lot wrong with the models that we have at the moment. So why do these models perform so badly? Well, I think there are four main reasons. I think, first of all, it's a question of the drivers of wildfire. So I think that there's many of the hypotheses that are incorporated into the models about what controls wildfire are not actually correct. Then I think there's the issue of stochasticity. The models are basically deterministic. They use a driver and they use inputs and then they come up with a burnt area. But both climate and wildfire are stochastic, and we have to learn how to deal with this. I think there's also an issue about complexity. I think the models, we keep on thinking about new processes that need to be incorporated into the models, but we don't necessarily consider the interactions between those processes and existing processes. And we often incorporate a new process and evaluate the overall endpoint, for example, simulated burnt area, without testing the processes independently. And then a final point that I think is important to make is about model tuning. The models that we're using to predict the future are tuned for modern conditions. They're tuned to reproduce the modern observations, but then we apply them into the future, and the future is a very different ballpark, but we're not actually testing whether the models can reproduce so-called out-of-sample states, so other climate states that differ from the modern. So what I'm going to try and do is quickly illustrate some new approaches to each of these problems. So first of all, hypotheses. So we do know some of the things that might control fire. And we can ask, what are the global drivers of wildfire? Now, the plot on the left here is showing the number of drivers that people think might be important in driving wildfires, and therefore they've built into empirical models. And the blue bar shows you how often these various things are incorporated into a model as a driver. And the red and the pink bars here show how often these particular drivers are selected as being important. So you can see that at a global scale, some people think that topography is important to include, or wind speed is important to include, or some indication of the impacts of demography on fires. And so they include those in their models, but those are not ever selected as being important. We can look at that in another way, and the plot on the right is doing that. Here is one single model, but a model which has been constructed to incorporate multiple different drivers and run for 1,000 times to see which of those drivers become important. And again, you can see here that there are some drivers that are consistently selected as being important. So the one right on the right is diurnal temperature range. There's the GPP, gross primary production, is always important in the model, but there are others, like the minimum temperature or the maximum temperature, which are never selected in these models. So what this is telling us is that many of the hypotheses that we think we know are important, things that are important for fire, and we therefore build them into our models, turn out not to be important at the global scale. So another thing that we can think about here is that most of the models that we use at the moment link burnt area, fire size, fire intensity, but you could actually think about whether these are being controlled by different things. So here's an empirical model built by Olivia Haas, which has made separate models for burnt area, observed fire size, and observed fire intensity. And you can see if you compare the observations with the predictions that the model to first order gets reasonable patterns for all of these. Much more smooth than in the real world because it is still a deterministic model, but nevertheless, at least showing the correct spatial patterns and magnitudes. The interesting thing about this is that when you then look at what is controlling these fire properties, the actual things that are important are very different. So we've got here 3 plots showing the importance of various drivers for burnt area, then fire size, and then fire intensity, and they're color-coded in terms of vegetation properties, human properties, and climate properties. And you can see from this that, for example, annual GPP, gross primary production, which controls the amount of fuel that's available for burning, is a very important positive influence on burnt area. But it has absolutely no impact at all on fire size. And in terms of fire intensity, annual GPP has a negative effect on fire intensity. You can look again at things like fragmentation. So we build into the model things like fractional crop cover or fractional road density in order to be able to take account of the fragmentation of the landscape, which might then have an impact on the types of fires that we see. And again, you can see here that roads do have a negative impact in terms of burnt area and on fire size, but they have a positive impact on fire intensity because of opening up areas where which would otherwise not have burned. And crops have a negative impact on both fire size and burnt area. So the area of crops fragments the landscape and reduces the burnt area, but has no impact on fire intensity. So this is important because it shows that we should be modeling the different fire properties in different ways with different drivers. Okay, there's one other thing that we need to think about here. I've already commented on the fact that it's not just the fire model, but it's also the interaction between fire and vegetation that's important to get things right. And one of the key things there is that CO2 changes have a direct impact on photosynthesis and therefore gross primary production and also on water use efficiency, and therefore have an important influence on the amount of fuel that is produced. So this is just a map that's showing recent greening trends due to CO2 fertilization and other factors like warming and increased precipitation. And the thing to take home from this is that over at least half of the world, possibly slightly more, CO2 is the primary driver of this greening and therefore this increase in fuel load. So that's the blue color that you can see on this map. Okay, so then we can say, what does that do to fire? We've had this greening, that's due to CO2. What does it do to fire? And here I'm introducing a paleo experiment to see what happens when we reduce CO2 in the last glacial maximum. So the last glacial maximum was the time that was about as different in terms of climate from us today as the end of the century is likely to be in middle of the road scenarios. So it's a good out of sample test. And what we've done here, again with Olivia's model, is that we've run a modern simulation with modern CO2. That's the top set of panels. We've done a modern simulation, but we've lowered the CO2 to an LGM state. And then we've done an LGM simulation, but with modern CO2. And then the final panel at the bottom there is a realistic LGM simulation with low CO2. And you can see that the CO2 has an impact on both the modern simulation and on the LGM simulation. Now, the nice thing about this is I can say, is this realistic? So here we have observations. The dots on these maps are observations of the change in fire between present day and the last glacial maximum based on charcoal data at individual sites. And the top panel shows you the realistic LGM simulation with both low CO2 and a colder, drier climate, whereas the bottom panel shows you what happens if you don't change CO2. And I think you can see here that the large observed LGM reduction in fire is primarily driven by the CO2 impact on fuel loads, which tells me that we have got the right response to CO2. And so if I now apply this model in the future, I can expect that the CO2 impact as well as the climate impact will be correctly attributed. So here are the future simulations. So again, if you look at the top panel, it's basically showing you by biomes what's going to happen to fire intensity, fire size, and burnt area in the different biomes in future under a high mitigation scenario and a low mitigation scenario. And then you can see the spatial maps that are down at the bottom. And you've got the realistic, as it were, simulation of the future, which has CO2, climate, and human activity factored in onto burnt area. And then you have the impact of what would happen with CO2 only, and then a map showing the difference between the two. And a key thing about this is that the greening and fertilization that we're expecting from increased CO2 in the future, which will then increase fuel loads, will have the impact on its own of substantially increasing burnt area. So this is something that's very important, that if we're going to make simulations of the future, we have to test whether our sensitivity to specific drivers is important, and we have to include CO2 impacts. Okay, now I want to look at stochasticity a little bit. So we can do modeling with a large number of predictors using machine learning AI techniques. One of the problems with this is you can throw in a large number of predictors, but you don't really know which ones are actually controlling things. So you're hoping for the best in terms of prediction. You can use the empirical models that I've just shown you with a set of predictors based on your hypothesized controls, which you have tested, but those are essentially they're not really stochastic, they're more deterministic models. So we want to think if there's a better way to model probability. And this is a new model that Theo Keeping has produced, which is looking at modeling the daily probability of wildfire occurrence in the US in a probabilistic way. And so here he's got a number of candidate predictors. He's doing a forward-backward variable selection to decide which ones are important. Then he's deciding which domains, i.e. which part of the range these things are significant or significant influence on fire. And then finally, he's putting this into a GLM, but using a power law transformation because GLMs tend to compress towards the mean. And here's the model that he arrives with. So the panel on the top shows model mean probability of a daily fire occurrence in the US, and then it's compared to the observed daily fire occurrence at the bottom. And what you see is that the model is now capable of reproducing the observations. As is the case with all models, it's somewhat more smooth than the actual observation. So there's some element of the stochastic behavior that is not being captured, but nevertheless, it is reproducing this chance of having a fire, which I think is an important thing. And I will say it's literally daily probability of a fire that's larger than 0.1 hectares. And the plot on the right just shows what are the most important controls on this daily probability. And you can see that at the bottom here, it's VPD, snow cover, precipitation, or antecedent precipitation, diurnal temperature range, rural population density, and gross primary productivity that come out as being important determinants of this probability. Okay, so that's one element of probability. That's the probability, the chance of occurrence. I think we're all quite used now to looking at predictions of what's going to happen to the weather today, the probability of rain today, or the probability in terms of seasonal predictions of weather events. These estimates of the probability, the chance of rain occurring, the chance of an extreme event occurring, are based on running large ensembles of simulations. And that's because we know that the climate itself is highly stochastic. So climate and fire are both stochastic. So what we can do here is to make use of these large ensembles and see what would happen if we took a typical year, but within all of the range of typical years that could occur under current climate. And this plot here shows under modern climate in blue and the 2-degree warming climate in pink, we've got 1,600 model years. And what you see is that Under the modern climate, we could have anything from 20,000 to about 60,000 annual fires in the US. Under a 2-degree ensemble, you could have anything from about 30,000 to nearly 120,000 fires per year. So there's a range that we could have. And again, we've got this model, run this model. So you've got the observed numbers of fires, you've got what you see from the reanalysis climate data, and then you've got what you get from an ensemble, a large ensemble, the mean here, and then the spread in that ensemble under modern climate. And we have the same thing for the mean state, the mean probability, and the spread under a 2 degrees warming. Now, obviously, if the more fire you have, the bigger the spread is likely to be, and that's what you see in those top two plots. But if you look at the spread divided by the mean, if you take out the importance of the numbers of fires, then you see that there are some places where the spread is very much larger than the mean number of fires. So there's an uncertainty, if you like, in terms of what might happen in these regions. And this also affects the potential fire season length. So again, looking at the ensemble under the modern, the top left-hand plot is the mean fire season length as predicted from this ensemble. But then we've plotted the maximum fire season length, and you can see that the maximum fire season length, even under modern conditions, could have been much longer than the mean. And when we go to the +2 degrees simulation, you can see that there's obviously an increase in the fire season length when it warms up, but the maximum increases even more. So there are some places in this set of simulations where the fire season length could be almost the whole year. Another way of looking at that is to sort of look at regions. The plots here, the colored bars on here, the colored distributions on here are in the modern day, the distribution of fire occurrence. And then the gray bars are what would happen in that region in 2 degrees of warming. There's two things I want you to take home from this. One is that the observed, which are the little lines that go across, in some regions, the observed maximum that we've had in the recent decade is within this distribution. So if you look at the marine west coast forests, the first one on the left, you can see that the red bar there goes through the tail of the distribution. So we've seen what the maximum might have been. But if you look at, for example, Mediterranean California, the maximum we've seen in the last decade is well below the range that we could have seen under a stochastic climate, modern climate, which means we've been quite lucky in some of these regions that we haven't had as bad a fire or numbers of fires as we could have had. Okay, so finally I want to come on to this idea about, can we reduce the complexity? When we build models, we put in a lot of processes. Each of those processes has to be parameterized. Each of those parameters has to be got from somewhere, from some observation. And many of those parameters are not very well known. So a few years back, Davansky wrote a paper that was quite challenging that said nothing in biology makes sense except in the light of evolution. And this has spurred a new generation of people thinking about vegetation models based on eco-evolutionary optimality theory. And the idea of eco-evolutionary optimality theory is that plants are optimally adapted to the environment in which they grow. And EEO hypotheses then are an attempt to determine the simple trade-offs that plants make in order to optimize their growth in those environments. So as an example of that, I want to show you the so-called P model, which is a universal model of gross primary production. And this is important from fire point of view because that is our fuel load, right? So the P model is based on two simple EEO hypotheses, the so-called least cost hypotheses, which says that plants minimize the sum of the costs of taking up CO2 for carboxylation, assimilation, and the water loss that incurs through transpiration. And then there's a coordination hypothesis, which says that the two rates that limit photosynthesis, the enzyme limited and the electron transport limited rates must be equal, otherwise you will not have optimal photosynthesis. And this yields a prediction of GPP based on two equations with no free parameters. And as the plot on the left shows, on the right shows, this model is capable with only two equations, no free parameters, to predict the observed GPP globally as measured at flux tower sites. And furthermore, the model is able to reproduce the seasonality of FAPAR, so the fraction of absorbed light, which also gives us the leaf area index. So the model, the PL model at the bottom here, reproduces that observed seasonality, and it does a lot better than the current models that we're using to predict impacts of climate change on GPP. So that leads me to the idea that we might be able to take an EEO approach to fire, and we can base that on the idea that we know that fuel load and fuel drying are the most important parameters to control wildfires. So we can hypothesize that the maximum difference between fuel load buildup and fuel drying is when fires might well occur. And we can then show that this is indeed the case in fire-prone environments. So the ones on the left, you can see there is a maximum distance between fuel buildup and fuel drying, whereas in less fire-prone areas, those two things coincide. Now, using these two simple seasonal relationships between VPD and GPP as a measure of fuel load and fuel drying, we can now try clustering the world in terms of those parameters to see what happens. And what we see here is that we can actually divide the world up into so-called regions that have distinct patterns in terms of those seasonal cycles of GPP and VPD. And then we can relate that to the fire properties within each of those clusters. So here we have 4 axes of variation in the fire properties, where fire properties is numbers of fire starts, burnt area, fire size, duration, emissions as a measure of intensity, and seasonal concentration. And then the dotted lines on these various graphs, which are showing the result of the RDA, are the clusters that we have derived. Remember, not taking any fire properties into account, but simply using VPD and GPP. And what you see then is each of these clusters has a distinct set of fire properties. So if you look, for example, at clusters 13, 12, and 11, they all have very high burnt area, but they differ in terms of fire size, they differ in terms of the number of ignitions, fire speed, fire duration, carbon emissions, and so on. So each cluster has a unique set of fire properties. In other words, what we're seeing here is a way of defining pyromes, fire regimes, just simply based on this concept of the balance between fuel loads and fuel drying. And then that leads me towards the idea of an EEO fire model, which is based on fuel load and the synchronicity between fuel load buildup and drying. And that gives us a measure which we're calling propensity to burn, which is the equation at the bottom there. Now we've applied that to develop the first step in an EEO fire model. What we've actually done here is to assume that the amount of GPP that goes to leaves and therefore to litter is constant everywhere. And we've also assumed that the decay constant of that litter is constant everywhere. And those are unrealistic assumptions, so watch out for this. But nevertheless, to first order, just with this very simple EEO scheme, we can predict the global patterns of fire. So you've got observed burnt area on the left and our simulated burnt area on the right. So what I'd like to finish with here is saying I think that the models that we're using at the moment are not really fit for purpose because they're not able to capture seasonality, interannual variability, or fire extremes. And then I think we need to revisit how we build realistic controls on fire properties into the models because our hypotheses are clearly not correct. And I will say I have built these fire models, some of these fire models, so it's my fault too. But we need to move forward with this. And then I want to stress that the controls on individual fire properties might vary and they might become decoupled under climate change. So we need to think about those separate properties. I want to also stress that vegetation properties are an important determinant of fire. So we need to think about that. And then I think it's very important that we move forward to model fire stochastically using probabilistic fire models and also using large ensembles. And I'd like to finish with the idea that EEO approaches may yield simpler fire models without losing predictability, although we've got a way to go. Okay, finally, I think there are a few challenges. So I'm going to say that building and testing this EEO global fire model is a challenge, that designing out of sample tests for global fire models is a challenge, that we need to think about incorporating fire management by people into the models because the fire regimes we see at the moment and we're training our models on do have fire management in, that we need to revisit the impacts of fire on the biosphere and climate. We also, I've only talked about global models here, but clearly there is a gap between global scale models and landscape scale models we need to address. And we need to think about being able to predict fire behavior in real time. And with that, I want to just thank my team in the Fire Veg Giraffe team who have made all of this work possible and will, I hope, be making it possible in the future. Thank you very much.
Okay. Yeah, thank you. Thank you very much. It's really comprehensive presentation on global Wi-Fi models. And I think we will now open it up for questions. And I see that there is an audience that, okay, thank you for great presentation. There's a one slide showing that dryness variables like VPD and humidity contribute positively to the burned area and fire size, but negatively to the fire intensive. Does it mean that some places might be beneficial from the global warming if we have better fire management on fire size, for example, in drier regions?
Yes, I think that's indeed the case. I think in terms of fire management, to me, the key thing to think about is reducing fuel loads before the fire season. So, because there's not a lot we can do about controlling VPD and drying, but we can control fuel loads. So I think techniques for controlling fuel loads are the key in terms of minimizing fire intensity and also burnt area.
Okay, okay, cool. Thank you. And okay, so as a host, I want to ask you a question. That you mentioned, GPP can represent fuel loads, but what do you think other like proxies like above ground biomass? And is it suitable to represent fuel loads? And I don't know whether do you have this input in your models before? What's the uh, effectiveness? What do you see the proxy for fuel load in models?
So I think that GPP is a good proxy for fuel loads because it does represent what's on the ground. So from the point of view of the litter and fire spread on the ground, it's going to be important for that. It also, the leaves themselves are going to burn. So once you have a crown fire and you're burning leaves, GPP is going to determine how much material there is. I think that one of the problems here, of course, is that if you just use GPP without trying to actually do the decomposition of the litter, then you have a problem because, and that's why I'm saying in our EEO model, we've used a standard, constant decomposition, and that's not realistic because decomposition varies with environment as well. So we do need to think about how you decompose the litter. I think the other thing that we need to think about is whether or not, so in terms of the moisture content of the leaves in crown fires, whether we actually need to simulate moisture content of the leaves, which we're not doing at the moment. We're just saying they're there. So those are two things I think would be important. And then I think the final thing that is not incorporated in this that we need to think about is the whole issue of ladder fuels. So it may be that the form of the trees themselves is going to be determining whether you move to a crown fire or not. But I think in terms of issues like how much fuel there is on the ground and how continuous that fuel is likely to be, then GPP is a good surrogate. Since it's very hard to know what the above ground biomass actually is, right? So
Yeah. Mm. But I've seen that there is also some data collection for above ground biomass. And I don't know whether did you use it before, like um
I've looked at it, yes. I mean, I'm not sure that it's well, okay, there's two things here. Number one, I'm not sure that it's reliable because the amount of actual field measurements of above ground biomass is limited, and so it's been extrapolated to come up with global products. The second thing
okay,
is
yeah.
if you're going to use this for prediction, you have to be able to simulate above ground biomass. And that means that you have to be able to simulate the allocation of carbon to below ground biomass, above ground biomass, stems, and so on. And that is quite a challenge to do.
Oh,
So it's
yeah.
something that should be done, but I think there's still a lot of work that needs to be done to actually get the carbon allocation correct.
Yes, yes, that's a problem in the future that we need to solve.
Mhm.
Okay, let me see what else. Okay, um, and there's an audience said, can this model be used for case studies? Could it be compared with a behavior model?
Uh, I don't think it's at an appropriate scale for a fire behavior model. I mean, I think this is why I'm saying that there is at the moment we're focusing on the global scale because in terms of prediction, it's knowing the global patterns that are going to be really important. But the local scale models and fire spread models are very different and are working on a much finer resolution, spatial scale. And so I do think there's some work to try and bridge things. I mean, one example of this is that in a fire spread model, wind speed is particularly important. When you're starting to look at sort of areas of, 10 kilometers squared, which is what most of your fire models are, that's good for a global fire model, then wind speed is not important because you're just using something on an average. So I think there is this issue of how things change along scales and then how we link global models to regional models to local models and then eventually to actual fire spread models in real time, which is what we need for fire management.
Okay, thank you. Thank you for that. And let's move on. Thanks. How about looking at the distance between LAI or NDVI peak and VPD peak? Same conclusion?
Um, well, I mean, we could use the LAI peak and VPD. I mean, that might be another way of doing it. It's one more step in terms of the modeling from GPP to get to the seasonal cycle of LAI. But that's something that we are investigating, whether LAI would be a better predictor than GPP.
Yeah. Okay, thank you. So next, if I understand correctly, you have measured observed fire intensity by dividing FRP by the square root of the fire size in each pixel. Have this measurement of fire intensity been validated or compared to ground data?
Um, it has not by me, but it has been used in that way and validated in observations. So I think it's a reasonable measure. It may be, I mean, as you notice, we use that for the original modeling, Olivia's original modeling. But what we are actually looking at now in terms of some of the model evaluation is the actual carbon emissions. So I think the carbon emissions are probably themselves a better measure of fire intensity or completeness of burn. I mean, the problem with, using fire radiative power is that it's an instantaneous measure. And what you really want is something that has um, an aerial kind of representation if you want to know how much has been burnt. So I think FRP is good for the sort of instantaneous measures. And by dividing it by the square root, we were trying to get a sort of intensity over an area. But I think probably the overall emissions are the things that we should be looking at.
Okay. Thank you. Hope this helps. Okay. Does the standardized GPP take into account increased rain events in some biomes as the climate change? For example, California has had heavy rains that caused large blooms, then intense drying that creates more fuels for fires.
So
Yep.
the idea of using this in prediction is that you are using, whatever climate inputs you've got from the model. So we're using a simulated climate when we're doing the futures, but that is taking account of whether there's going to be changes in precipitation or whether there's changes in the seasonality of precipitation. So yes, the GPP model is actually taking that into account, and the fire models are also taking that into account. Now, I mean, I think one of the things that I was showing in that probability model is you can see already in terms of fire that there have been very large shift in the last 3 decades in terms of the fires. And I think that does reflect these changes in recent climate.
Okay. Thank you. Thank you very much. Is there any other questions? Um, okay. Okay. Um, so let's just wrap up for today's session. And I want to thank you all for joining us, and a special thanks for Professor Sandy Harrison for this enlightening presentation. And yeah, so before we sign off, please keep an eye out for this webinar evaluation that will be sent out later. Thank you once again, and I look forward to seeing you all in these future sessions. So have a great day. Thank you. Bye.
Thank you, Henry.
Oh,